All right. Now, please look up. We'll be looking at glucose to amino acids translocation with sodium ion in the membrane. We are going to look at how amino acids are translocated by sodium ion through the membrane. Now, let's start. If you look at this side, this is the cell membrane. And these big stuffs here, they are transmembrane proteins, transporters. This is the extracellular matrix, that is the outside of the cell, and this is the inside of the cell. You agree that the cell membrane, the plasma membrane, is the barrier between the outside and the inside, right? Now, take note that sodium ion is always high outside the cell than inside the cell. So the concentration of sodium ion is high here and is low here. So sodium is moving now from high concentration to what? Low concentration, right? It's moving from high concentration to low concentration. Is that active transport or passive transport? Passive transport, right? Now, you may be tempted to forget, is sodium high inside the cell or low outside the cell? I was passing through that until I told myself one day, I was like, sodium is a positive ion found in salt or sodium chloride. Does it mean that in this world outside my body now I have more salt, or I have more salt inside my body? Do you have more salt outside or inside? Outside, right? That was the nonsense I used. Okay, salt is more outside than inside. So I use that nonsense to say sodium ion is always high outside the cell than inside the cell. Now, the movement of the transport of sodium ion from outside to inside is moving from high concentration to low concentration, right? Meaning it's moving with concentration gradients. And as it is moving with concentration gradients, something called sodium motive force will be generated, SMF. And this sodium motive force generated from the transport of sodium ion with concentration gradients will provide the energy that is needed for the transport of either glucose or amino acids into the cell against concentration gradients. Now look at this. Sodium is high here, it's low here. So moving from high to low, we are moving with concentration gradients. As we move sodium outside the cell into the cell, sodium motive force is generated. And this sodium motive force is the energy that fuels the transport of some of the molecules like glucose, like amino acids into the cell. Now, in the case of glucose is high inside the cell than outside the cell. Glucose is low here, glucose is high here. And we want to move it from low to high. It means we need energy, right? For you to move glucose from low concentration to high concentration, energy is required. And what is moving it from this low to high is the sodium motive force generated. So this is the sodium glucose transporter. This protein here is the sodium glucose transporter. That for every 2 molecules of sodium ions transported into the cell, 1 molecule of glucose is transported alongside against concentration gradients with the same port mechanism. If you come down here, you see sodium ion. Yeah, in this case, the sodium ion moving with concentration gradient or against concentration gradient. Is it with or against concentration gradient? Okay, this is sodium ion. All right. Now, observe this. So, sodium ion is always coming in for glucose to be coming in, right? Is the sodium ion that is for this transporter to bring glucose in. Sodium ion must produce that sodium motive force, right? Now, just take for example, sodium keeps on coming, and nothing is removing the sodium. You notice that it will get to a time when the sodium ion inside will not exceed what is outside, because it's one directional, which is bad. So to maintain the level, we have what we call the sodium potassium ATPs. Sodium potassium ATPs, or you call it sodium potassium exchanging ATPs. Now, these sodium potassium ATPs, for every 2 molecules of potassium ion coming into the cell, with concentration gradient. 3 molecules of sodium are sent out against concentration gradient. For every 2 molecules of potassium coming into the cell, how many molecules are sent out? How many molecules of sodium? 3 sodium ions are sent out of the cell, right? Now, in the process, ATP is broken down to give ADP, an inorganic phosphate. That is why we call it ATPs. ATPs. So, this structure on the board here explains glucose or amino acid translocation with sodium ion. So, take note that for every 2 molecules of sodium entering into the cell, we said sodium motive force is generated, right? That can transport how many molecules of glucose into? 1 molecule, right? And to maintain balance, for every 2 molecules of sodium or potassium ion entering, how many molecules of glucose is? How many molecules of sodium ion? 3 molecules are sent out of the cell by the sodium potassium ATPs. So if you're asked in exam, please draw this. And after drawing this, you can say from the diagram above, for every 2 molecules of, as 2 molecules of sodium moves into the cell, sodium motive force is generated to pump glucose into the cell against concentration gradient. Now, to maintain balance, we said for every 2 molecules of potassium entering, 3 molecules of sodium ions are sent out of the cell, right? And in the process, ATP is hydrolyzed. This is catalyzed by sodium potassium ATPs. This one is sodium glucose transporter. Now, if you have glucose in uniporter, uniport means 1 molecule transported, right? Now, the transporter now, glucose uniporter is that protein, that transporter that transports glucose alone into the cell. It's not transporting it with sodium. It's not transporting with anything. Glucose is a lone ranger here, moving alone through the transporter. And remember the steps involved in the transport of molecule. First, depending on where this cell membrane is it in the plasma, is it in the brain, is it in the erythrocytes, it will determine the glucose transporter that will be used here. Remember, we have 5 isoforms. So now, the substance, this transporter will recognize the molecule, and if you see, oh, this is glucose, this is what I was supposed to transport. The glucose will bind to it, and there will be a conformational change, right? Allowing the glucose to pass through it. Then from here, the glucose will be released into the cell, and the shape of the molecule returns back to normal. So basically, this is glucose amino acid translocation. Now, let me ask the question. What if this sodium potassium ATPase is inhibited? What do you think will happen? If the sodium potassium ATPase is inhibited, what do you think will happen? If this is inhibited, you know sodium ion will not be sent out, right? So the sodium ions will now be located here, will now be more here. And as it's now more here, sodium motive force cannot be generated, and so glucose cannot even be transported into the cell, because it's actually the sodium motive force generated by the transport of glucose with concentration gradient that was driving the transport of glucose. So if this one is inhibited, sodium ion will accumulate here, so we'll now have a higher concentration here than here. So moving from here to here is no longer passive transport. So glucose cannot be transported into the cell if this one is inhibited. So basically